Hi guys, please like, share and subscribe and contact this number if you want lectures related to any CM, CS or CB subjects. Thank you.
In this video, I am going to talk about a very simple yet very powerful mathematical technique that is used in actuarial exams, that is linear interpolation, right? So, I am going to address particularly three issues in this video. The first one is why or where do we need linear interpolation? Second, the maths of it, and the third is the exam application, right? So, let's just get into it, okay? So, firstly, where or when do we need linear interpolation in exam questions, right? Well, it's fairly simple, right? It is whenever you have a function of some variable x, which is let's call it y, right? And you only know the value of y corresponding to x for a subset of values of x. Typically, this is integer values, or it can be any particular values of x against which you know y. Let me explain this through an example. Okay. In our actuarial tables, you would notice that there is a function which is called as Lx, right? This is the typical, what is the number of people alive at different ages, right? For different actuarial tables. If you have studied subject CM1, you would have seen Lx. Now, Lx is a function of x which is age. Now, I typically only know Lx at integer ages. So, I would know it at the age of 20, I would know the value at 21, I would know the value at 22, I would know the value at 23, so on and so forth. So, for ELT 15, it goes up to about 110, right? So, this is how, and in fact, for ELT 15, it starts at 0, right? So, for all of these integer ages, I know different values of Lx. These are known to me, right? So, I know a value here, which maybe let's say is 10,000 is what we start with at 0, right? And by the age of, okay, so let's say at 0, I know 10,000. And then by the age of 20, it is some 7,000. And then at 21, another 200 people die. So, let's say this is 6,900. Here it is 6,750 or something, and so on and so forth. So, basically what is happening is, you know that Lx is falling with age, right? Because the number of people in your insured cohort would fall, right? But you only know it at integer ages, right? So, you only know y, which is Lx in this case, corresponding to a subset of values of x. And in this case, if you want to find out your y or Lx at any of non-integer ages, let's say you want to know your Lx at the age of 22.5, then what do? Lx is not available at the age of 22.5. L 22.5 is not known. So, then how do you get it from this? That is where your linear interpolation comes in handy. And you use linear interpolation to find the values of y. For the values of x, it is not given, right? So, if it is only given for a subset, then how do you find it for the rest of the values? That is the broad idea of linear interpolation, right? Now, let us talk about the maths of it. What do I do here exactly, right? So, I know that Lx is a decreasing function. I know that it is falling in some fashion, right? If I am to apply linear interpolation, what I broadly do is I take an assumption. And what is that assumption? I take the assumption that Lx or y generally moves linearly, that moves meaning increases or decreases, or you can say changes, it changes linearly between integer ages. So here in this case, what I would end up assuming is that between these ages where I do not know what the value of y or lx in this case are, I would just assume that to be them to be linear or straight lines. So I will just assume that there is a straight line here, and then there is a straight line here, and then there is a straight line in the next one, so on and so forth. So I assume that between integer ages or between the given subset of values of x, your value of y changes linearly, that is, it increases or decreases linearly. I assume these to be straight lines. What does that mean intuitively? Well, intuitively, it just implies that what we are saying in this case is that if there were, let's say at L20 you had the value 7,000. So there were 7,000 people alive at the age of 20. L21, let's say, happens to be, as we took, 6,900. And if I am to find L20.3, what would that value be? I would just assume that between these two ages, these are number of people alive. So I would assume that 100 deaths have happened, right? That I know, that 100 deaths have happened. I would assume these deaths to be linearly distributed throughout the year. So if I am to find out what are the number of people who have died by the age of 20.3, if 100 deaths happened in 1 year between 20 and 21, how many deaths would have happened in 0.3 of the year? Well, that would be simple, 100 into 0.3, that is 30 deaths. I can just say that 30 deaths would have happened in this year. So your number of deaths by age 20.3 is simply equal to 30, right? That's a reasonable assumption, right? So I've assumed that deaths are distributed linearly throughout the year, right? So if 100 deaths happen in 1 year, then 0.3 of a year, 30 deaths would have happened. Now that's not necessary, that may not be realistic, right? It can happen in 0.3 of the year, about 50 deaths have happened, and the remaining 0.7 of the year, another 50 deaths has happened. But we do not know that. So one of the good assumptions to take here is to assume that the deaths are distributed linearly, and in 0.3 of a year, 30 deaths have happened. In half a year, 50 deaths have happened. In a quarter, that is 0.25 of a year, 25 deaths have happened. And that is just your linear interpolation. Now, how do you apply it in this case? So let's again try to understand that intuitively. So if I am to calculate L 20.3 in this case, how will I get that? That will be equal to 7,000 minus the 30 deaths that have happened, because deaths are happening and number of lives are reducing. They are going from 7,000 to 6,900. 100 deaths happen throughout the year. In 0.3 of a year, 30 deaths happened. So your L 20.3 would be equal to 6970, right? If I am to calculate L 20.5, that would be 7,000 minus 50, that would be equal to 6950. And finally, if I am to calculate L 0.20.25, that would be equal to 7,000 minus 25, that will be equal to 6975, right? So this is how you can get these values. Now, obviously here I explained the whole thing intuitively. Now let's see how do you apply this in exam, or what is the generalized formula for this, right? So for that, first I'll just take a simpler example. Here, see, the complication is that there is a decrease that is happening. Well, that is not a complication, it's not a great way to construct a formula. It's not a great case to construct a formula. We are going to take a case where there is a linear increase that is happening, right? So let's talk about such a case. Okay, let's say you have values of x. Okay, so you have values of x as 1, 2, or let me make it 10, 20, 30 and 40. Against that you have values of y which are, let's say 27, 38, 46 and 72. These are the values of x and y that you have, and you have been asked, you have to calculate y when your x is equal to 27. Okay, this is the question that has been given to you. So how do you proceed in such a scenario, right? You have to calculate y when x is equal to 27. Okay, so now what do you know? You know a couple of things. You know that y equal to 27 will be between 38 and 46, right? Why? Because x, when x is 20, your y is 38. When your x is 30, your y is 46, right? So between 20 and 30, your y is increasing as x increases, right? So the value has to be between 38 and 46. So firstly, you decide on what bracket do you want to linearly interpolate. Now here you want to interpolate between 20 and 30, right? And your answer will be between 38 and 46, right? Now how do you do it, right? So you know that the value is going to be larger than 38, right? So you start with 38. So you say 38 plus, because I want to go higher from 38. Now how much higher from 38 do I want to go? Well, if I was to go from 20 to 30, right, in terms of x, if x was to go from 20 to 30, then y would go from 38 to 46. So it would go 8 points higher when x goes 10 points higher, right? That is how you can think about it, right? So the entire distance that you would have had to cover would have been 8 points in terms of y. So if you would have gone from 20 to 30 in terms of x, but you are only going till 27 in terms of x, right? So how do you do this? You say that I want to go 8 points higher, that is 46 minus 38, 8 points higher in terms of y. But I do not want to go entirely, I want to go a proportion of it. Now what is that proportion? That is the key. I want to go only as much as till 27. I don't want to go all the way up till 30. I want to go only as much as up till 27, right? So what is the distance between 27 and 20? That is 27 minus 20, that is 7 points. Out of the entire distance, that is 30 minus 20, right? So this would give you your answer, which would be 38 plus 8 multiplied by 7 by 10. Now 8 times 7 is 56, by 10 is 5.6, so it would just be 43.6. This is how you do your linear interpolation. Let me repeat what I did. I just found the starting point. Where did I have to start in terms of y? Because when x is at 20, y is 38. When x is at 30, y is at 46, right? You want to cover this distance, but only partially. You only want to go till 27, right? So I started at 38. I said that the entire distance that I would have had to cover between 20 and 30, if x was to go to 30, would be 46 minus 38, right? That is 8 units. But I don't want to cover this entire distance. I just want to cover a proportion of it, which is your till where do I want to go? I want to go till 27 from 20. So 27 minus 20 divided by 30 minus 20, that is your total distance, right? So this is the ratio I will take on this, and I will thus reach this amount of ratio in terms of y, right? Here if you notice all the variables that have been I'm starting at a point of y, I'm covering the distance in terms of y, I'm just applying a proportion that y only goes much as further as x has. So that's the idea. Now let's just generalize this formula. If I am to generalize this formula, I can just write this as, if I have to go from y1, the starting value is y1, the ending value is y2, y1 is corresponding to x1, y2 is corresponding to x2, and let's say I want to find some y0 corresponding to x0, then what will it be? It will be equal to, y0 is equal to, I will start at y1, I will say what is the distance I have to cover, that is y2 minus y1, right? But what proportion of it? Only part of it up to x0, right? I just want to cover this part of it out of this whole thing, right? So I will just say x0 minus x1 divided by x2 minus x1. This is your generalized formula for linear interpolation. This is how you apply it, right? Just take what is the total distance in y, apply the ratio. What have you covered in x? You will cover the same volume or same units in y, right? Okay, now the beauty about this formula is that it can handle increases and decreases both, right? So let's say in our previous example where we had your L20 was equal to, let me go and see what was 7,000, and L21 was equal to 6,900. Here we have decreases happening and we had to calculate L20.3, right? How do I apply this formula? Well, I have to start at 7,000, right, which is your y1. So 7,000 plus y2 minus y1, which is 6,900 minus 7,000. This is the entire distance that I have to cover, right? But I want to cover only a proportion of it, right? So what is the proportion of it that I want to cover? Well, I want to cover only this much of it, right? Which is, where do I want to go? What is my x0? Well, my x0 is 20.3, right? From a scale of 20 to 21, it is 20.3. It would be somewhere here actually, right? So I want to go to 20.3. So this is 20.3 minus x1. What is x1? That's 20 divided by 21 minus 20, right? So now if you take this, what does this become? This becomes 7,000. 1,600 minus 7,000 is minus 100. So minus 100 multiplied with, what is this? This is 0.3 by 1. So that's 0.3. And thus this is 7,000 minus 30, which is equal to 6,970. So this works with increases and decreases both.